Welcome to Rationality, Reason, and Reality. I'm Supernova. In the next few videos, I'm going to be discussing why 0.9 repeating doesn't equal 1. This is a point that I've already tried to make before, but I don't think I made it as solid as I'm going to do here. I took too many assumptions, figured out that people would understand where I was going, and so people kept commenting with all these objections that I keep giving the same answers to, and most of them were irrational. Now, it seems weird that I'd be arguing against this because if you're familiar with the argument, the consensus among expert mathematicians is that 0.9 repeating does equal 1. It doesn't seem the sort of thing that a rational person would argue against. But there are contradictions in their arguments. There are ways that they use infinity one way and use it another way. And they don't seem to understand that they've created these problems for themselves. So I'm going to discuss the way I see infinity, how I came to these conclusions, and I'm going to lay down a more solid foundation and do this over a further length of time. And I think I will make a more solid case this way and convince you whether you disagree with me or don't know the case. I would suggest that you actually see another video on how mathematicians believe that 0.9 repeating does equal 1, at least hear their arguments before you hear me try to deconstruct them. So in this video, I'm going to specifically be tackling 3 myths about infinity, 3 things that mathematicians and the general public tend to get wrong about infinity. Number 1, the belief that math is all about deductive logic. Now, practically any time that I lay down my case, and I will in the next video, I'll discuss how inductive logic can be used in math, and this is kind of revolutionary, even though it has been done. Everybody does it. You've probably done it, and I'll show you how. But most of my conclusions about infinity are drawn from induction, which is typically used in science, not in math. Math is usually based on deductive logic. Now, if you don't know what I'm talking about, I did make a video on this, basics in logic, in an earlier Rationality, Reason, and Reality video. But just to give you a quick primer, deductive logic takes a general rule and you draw data points from it. For instance, if all cats are mammals and Garfield is a cat, then Garfield is a mammal. If all cats are mammals and Felix is a cat, Felix is a mammal. You take these general rules that all cats are mammals, and then you take specific cases of cats. You can figure out the cats are mammals. This is taking what's already known and making data points out of it. You don't have to know Garfield or Felix or anything to know that they are mammals. They follow this general rule. Given all the information that you have, you can come to that conclusion. Now, inductive logic is what science uses because science doesn't know how nature works. All they can do is just observe different examples of how it works and try to build a basic rule. For instance, they might find this cat named Garfield and find out that he's also a mammal, and they might find this cat named Felix and decide that he's also a mammal. And so they might build this general rule that all cats are mammals, which was a premise in the deductive argument. But since we don't know it to be except from the data points in inductive logic, it's built the other way. Now, it might not be the case. Inductive logic isn't as solid as deductive because we might find Scooby the cat who isn't also a mammal, and then we would find that not all cats are mammals and our rule would be broken. But until you find counterexamples, it is a good rule. It is logic. It's reasonable to follow that path. Now, when we're talking about math, typically we talk about things like proofs, which are all built on deductive logic, and even just basic math that you do, like addition, is built on deduction. You don't actually have to go out and add things and find more examples to figure out the rule. It's already been done. It's axiomatic. It's already accepted as a general rule, and we use that for addition. But there are cases where we use inductive logic. Consider this thought experiment. Let's say that we're sending 3 probes out into space. One's going 20 miles an hour, one's going 40 miles an hour, and the third one's going 60 miles an hour. And yes, I'm an American. That's why I'm using miles per hour. Now, we know that what the speeds are because I just gave it to you. This is an accepted part of the thought experiment. So you could graph their change in distance over time because you know the speed, which is distance over time, and you could figure out their distance given any time or the time it's taking them to get any distance by looking at your graph. But what if you didn't have these speeds? What if all you were doing was observing them as they traveled, and you noticed that they're at this one certain point at one time, then after another time they're at this other point, and then after another time they're at this point? Well, you could still graph it. You do the same thing. You just, instead of giving their speeds, you would figure out their distance over time manually by all these different examples. That's inductive logic. You're doing the same problem but from a different angle. Another example, and probably a little more pertinent to infinity, are things like dividing 1 by 3. If you do it longhand, you know that you get 0.3, and then you have a remainder of 1, which you drop and add a 0 to, and then you divide that by 3, and it gives you a remainder of 1 that you add a 0 to it, and divide it by 3, and you get 3, and you drop 1, and add a 0 to it, and this pattern continues. So you can tell that this pattern is going to keep going on, even though you can't do the problem to its end. You'll never be able to do it because you would have to have an infinite amount of time just to write those infinite 3's. But you can see from the individual data points, the first division, and the second division, and the third division, and the fourth division, they all seem to follow this pattern, and so you know that this pattern is going to continue, and that is inductive logic. You figured out that 1 divided by 3 is 0.3 repeating inductively. And this is very close to the inductive logic that I will demonstrate in the next video, where I show how I've come to the conclusion that 0.9 repeating doesn't equal 1. And how you can actually multiply and divide such infinite sums. Myth number 2: not all infinities are the same size. Now, this isn't revolutionary. Mathematicians will agree with this. The very first video I saw on this that sparked my interest and made me see that there are some problems with math was a minute physics video, which discussed how to count infinities, and it described the difference in size between all the integers, the numbers 1, 2, 3, 4 going infinitely, and the real numbers between 0 and 1. And it claimed that there were two different sizes. There are more numbers between 0 and 1 than there are 1 going into infinity, and it's true. And I actually figured it out a different way than they demonstrated. I thought their proof was kind of flawed, and they didn't actually follow the rule that they had demonstrated. But nonetheless, there are different sizes in infinity, and mathematicians get this. But what I seem to get from several of the mathematicians I've argued against is that they only believe that there are these two sizes. They believe something like integers are a size that they call countless, which is an infinite length, but not as infinite as infinity. And they keep trying to make all these arguments that all infinite lengths are the same. For instance, a lot of mathematicians believe that there are just as many numbers from 0 to 1 as there are from 0 to 2. They get this by multiplying all the real numbers between 0 and 1 by 2, and they say all of those numbers are found between 0 and 2, and so you have a 1-to-1 correspondence, and so there are just as many in one set as there are in the other. Does anybody else find this to be a little odd? I mean, if you had a 1-to-1 correspondence, just everything from 0 to 1 would also be found in 0 to 1 in 0 to 2, and you'd still have everything between 1 and 2 that didn't have a correspondence. It seems like a paradox. Whether you did it one way or did it another way, you'd come up with different answers. One, it's even, and one, the second set is twice as large. Consider this. Instead of something abstract like just numbers that are multiplied by 2, let's look at what it would look like if we drew it out. Here's just your typical Cartesian plane. We have line A, which has all of the numbers along the y-axis, all the real numbers between 0 and 1, and line B here has all the numbers, the real numbers between 0 and 2. Instead of just numbers, they're points on the y-axis. Why would anybody argue that these are the same lengths? That's absurd. Of course B is twice as long as A. It's obvious. Now, it would seem from this that either there were numbers between 0 and 2 that couldn't be divided by 2 and thus wouldn't be found between 0 and 1, or if they were divided by 2, they wouldn't be found between the real numbers between 0 and 1. And that is what I'm going to argue, and I will demonstrate that in a later video. And also considering the thought experiment with the probes. If you were to give them an infinite amount of time, they would all be infinite distances, but not the same distance. Obviously, the one that's going 20 miles per hour will be half the distance of the one going 40 miles per hour. This is something we can figure out from induction. Given any amount of time, any finite amount of time, something we can calculate, you'll always find that the second probe has gone twice the distance. Why would we think that given an infinite amount of time that the first probe will suddenly have caught up to the second one, that they will have gone the same distance? That's just silly. The third myth is that infinite is synonymous with maximum. It seems like the largest possible thing that we can think of, but obviously it's not. Going back to this thought experiment a third time, the probe that has gone 20 miles per hour after an infinite amount of time has obviously not gone as far as it can. The other two probes will have gone two different further distances, and we can picture any speed much, much faster than these other ones that will have gone further distances. Something with an infinitely fast speed will have gone a much further infinite speed, but that isn't even the fastest we can go, because they're infinite is just a trait. It's just a way of thinking of something, but it doesn't mean the most. It doesn't mean the maximum. You can have something longer than an infinity. You can have a bigger infinity, because infinities come in different sizes. So I hope I've given you some food for thought, and in the next video I'll get a little more into my actual theory, where I discuss how you can use inductive logic to figure out math problems, and we'll be discussing why it is clear that 0.9 repeating does not equal 1, doing some math that mathematicians will tell you can't be done or they're unwilling to do. Anyway, until then, comment, subscribe, peace out.